Good evening, students. So now let us just discuss about the MOSFET. So MOSFET is one of the power transistors, and it is very well used in the fax devices. So let us see the construction, working principle, classification, and the transfer characteristics of MOSFET. So MOSFET is the metal oxide field effect, metal oxide semiconductor field effect transistor. Field effect transistor. So coming to the MOSFET, first let us just see the construction of MOSFET. So we know in general, we have two types of semiconductors, semiconductor materials, P-type and N-type. So here, if the substrate is a P-type substrate, so substrate can be imagined a tub-like structure. So if this is a P-type substrate, then the opposite layers are immersed on either ends of the substrate. So if the substrate is P-type, then the immersed regions are N-type. So it is immersed on either end of the region, and a silicon dioxide layer is grown throughout the N region. So this is the silicon dioxide layer, SiO2. And now it is cut through this N region so as to form the source and the drain terminal. So one terminal is the source and the other one is drain terminal, and it is cut through the silicon dioxide layer and it reaches the N layers which has been immersed in the P-type substrate. Whereas the third terminal, which is named as gate, is present above the silicon dioxide layer, and it is this gate which controls the operation of the device. So the depletion capacitance that is formed between the channel. So this part we used to say it as a channel through which the charge carriers move from source towards the drain. So this is called as the channel. And since the immersed layers are N-type, so we call this as the N-channel MOSFET. So this is a N-channel MOSFET. So the silicon dioxide is forming a dielectric medium, and on one side it is negatively charged, and the other end is the gate terminal. So two conducting plates separated by a dielectric medium acts as a capacitor. So it is this depletion capacitance which is controlled by the gate voltage drives the device. So this is in case of the N-channel MOSFET. So same way we can imagine for a P-type P-channel MOSFET. So if it is a P-channel MOSFET, then the substrate is of N-type, and the regions that are immersed on either ends are P-type regions, and a silicon dioxide layer is grown throughout the region, and this is the SiO2 layer. And the same way as it has been shown in the previous case, the terminals are cut through the silicon dioxide layer in order to have the source and the drain terminals. So source and the drain and the gate terminal. So the gate terminal is in the net. So where now we have the P-type channel on one side, and on the other end we just have the gate terminal, and it is this SiO2 dielectric medium which is controlling the depletion capacitance which drives the device. So the gate source voltage is the controlling factor. So that is why metal oxide semiconductor field effect transistor, so called as MOSFET, is also called as voltage controlled device. So this is about its construction. So coming to the classification. So MOSFET can be broadly classified into two types. One is depletion type MOSFET, depletion type, and the other one is enhancement type. So again, this depletion type MOSFET can be classified into N-channel MOSFET and P-channel MOSFET. And this depletion type MOSFET has two modes of operation. One is depletion mode and other one is enhancement mode. Coming to the enhancement type MOSFET, again, it is of P type and N type. So first, let us see in detail the working principle of the depletion type MOSFET. So coming to the depletion type MOSFET, the symbol is so this is the source terminal, the drain terminal, and this is the gate terminal, and this is the substrate. And here, the space which is present between the channel and the gate terminal denotes the presence of silicon dioxide layer. So if it is pointing towards, so this will be the N-channel MOSFET. And the other way, we just draw the P-channel MOSFET. Then, coming to the depletion type, let us take the MOSFET circuit. So let us take the explanation for the N-channel MOSFET. So here, we have the gate terminal and we have the source terminal, the drain, and the drain source voltage. Then we have the substrate, which is P-type substrate. Then we have the gate source voltage, which we take it as VGS. And this is the drain source voltage. And now, this is the diagram for a N-channel MOSFET. So coming to the depletion type MOSFET, it operates for all the three values of gate voltage. Whenever the gate voltage is equal to 0, there is a minimal flow of drain source current, which is so-called IDSS. So that is why this depletion type MOSFET is generally called as normally on MOSFET. So due to the existence of a minimal current when the device is put on, so it is called as normally on MOSFET. So when the gate voltage is negative, we mean to say that here this is negative, this is negative. So thereby the other plate is induced to be positive. Now the charge carriers, whichever is released, which is of N type, released by the source terminal, will be combining with the positive polarity. So thereby there is a deplete in the N charge carrier, N type charge carriers reaching the drain current. So thereby the drain current reduces in its magnitude. So whenever VGS is negative, positive polarity is induced in the other plate, as a result of which the N-type charge carriers released from the source is not reaching the drain, and rather it is combining with the positive polarity charge carriers. So due to this, whenever the gate source voltage is negative, the drain current reduces in its magnitude. When the gate source voltage is positive, we mean to say that this is positive. So if one plate of the capacitor is positive, then obviously the other plate of the capacitor will be negatively charged, due to which the negatively charged carriers are induced internally in addition to the charge carriers released by the source. So thereby, there is an enhancement in the charge carriers, thereby increasing the magnitude of the drain current. So in the previous case, it is deplete of the charge carriers. So that is why it is called as depletion mode. Whereas when the gate source voltage is positive, it is having a enhancement in the drain current. So the drain current increases in its value. So thereby, this is called as enhancement mode operation. So that is how the depletion type MOSFET works for all the three values of gate source voltage. So now let us see the transfer characteristics. So the transfer characteristics is drawn between the gate source voltage and the drain current. So the drain current is taken along the y-axis and it is measured in milliamps, and the gate source voltage is taken along the x-axis. So since it is working for all the three values of gate source voltage, we have positive gate voltage, zero gate voltage, and negative gate voltage. So as it is said already, whenever the gate source voltage is zero, it is the minimal drain source current that exists, which is IDSS. So this is given by IDSS. So when the magnitude is increased in the positive way, when the gate source voltage is increased in its magnitude positively, then from this value of IDSS, the drain current increases gradually, which is called as enhancement. So this is the enhancement mode of operation. Then when the drain current is increased in the negative side, the drain current decreases from this IDSS value and steeply gets reduced and reaches zero value at one instant due to the deplete in the charge carriers. So this mode of operation is called as depletion mode of operation. So this is called as the transfer characteristics. This is the transfer characteristics. So what do you mean by transfer characteristics? So transfer characteristics gives you the idea how the gate source voltage is controlling the overall operation of the device and in what way it is controlling the output current, which is the drain current. So in this depletion mode of operation, it operates both in the depletion mode and enhancement mode. So it works for all the three values of gate voltage. So for zero gate voltage, there is an existence of a minimal drain current, which is IDSS. And for positive gate voltage, there exists the value of drain current and there is a steep rise in the drain current starting from IDSS and it reaches the maximum value. And it is increasing with the increase in the gate source voltage in the positive manner. Similarly, if the gate source voltage is negative, then the drain current reduces from this IDSS and it gets gradually reduced as the gate source voltage is more and more negative. So this is called as the transfer characteristics. So now let us see the drain characteristics. Coming to the drain characteristics, It is the characteristics drawn between the drain source voltage and the drain current, which is measured in milliamps. So this is taken for various standard values of gate source voltage. So say for example, if this is IDSS, then if this is the VG is equal to -2, VG is equal to -1, then VG is equal to 0, which is equivalent to IDSS. Then positive gate voltage at which VG is equal to 1 volt and VG is equal to 2 volt. So it is this which gives the enhancement mode of operation, and this is the depletion mode of operation. So drain characteristics is the characteristic which is taken between drain source voltage and the drain current. So drain source voltage is taken along x-axis and the drain current is taken along the y-axis, and it is drawn for various constant values of gate source voltage. So it is very well clear that IDSS is a minimal value that exists when VG is equal to 0, and when the gate source voltage is increased in the positive manner. For the given gate source voltage, the drain current increases and gets saturated in its value. So likewise, when the gate source voltage is made more and more negative, it decreases in its value and gets saturated for the given gate source voltage. So this is the drain characteristics. Now, coming to the enhancement type MOSFET, it works only for the positive gate voltage. So before we just switch over to the enhancement type MOSFET, let us just look a glance regarding the MOSFET construction. So we have just discussed about the construction of the MOSFET and how it has been named as N-channel MOSFET and P-channel MOSFET. Then we have just seen what is the classification of the MOSFET. So the broad classification is depletion type MOSFET and enhancement type MOSFET. And again, under the depletion type MOSFET, we have N-channel MOSFET and P-channel MOSFET. And whatever might be the type of the MOSFET, under the depletion type, further there are two modes of operation. One is depletion mode of operation. Another one is enhancement mode of operation. So enhancement mode of operation is for positive and zero gate voltage, whereas the depletion mode of operation is happening for the negative gate source voltage. So then we have just seen the working principle of N-channel MOSFET and the transfer characteristics, in which we are able to observe that there is an existence of a drain source current even when the gate source voltage is 0. So that is why this depletion type MOSFET is generally called as normally on MOSFET. And in the transfer characteristics, we are able to observe clearly how the gate source voltage is affecting the drain current, both in the positive direction as well as in the negative direction. So when the gate source voltage is incremented in the positive direction, the drain current increases steeply, whereas in case of the gate source voltage increase in the negative direction, it reduces the drain source voltage, and at one instant, it makes the drain current to become 0. Then we have just seen about the drain characteristics, in which it is drawn between the drain source voltage and the drain current for various constant values of gate source voltage. We have just seen that for the given gate source voltage, there is an increase in the drain current, particularly for the positive values of gate source voltage, whereas for negative gate voltage, the drain current reduces from the threshold value of IDSS and gets saturated at an value. So next, let us move to the enhancement type MOSFET. Coming to the enhancement type MOSFET, this enhancement type MOSFET differs in its construction itself. So in case of the depletion type MOSFET, we have a physical channel. So there are salient features to be noted under this enhancement type MOSFET. So the very important feature is that, so it works only for positive gate voltage. And secondly, it doesn't have a physical channel. So no physical channel is available in the enhancement type MOSFET. And that is why it is called as normally off MOSFET. Since it doesn't have the minimal value of IDSS when VG is equal to 0. So if you take the N-channel MOSFET, we can just take that. This is how the substrate is extended throughout. So gate terminal, source terminal, drain terminal. And this is how it is connected. So this is the drain and source voltage. And this is the gate and source voltage. So the substrate is extended throughout and it works only for the positive gate voltage. So coming to the transfer characteristics. So while you are taking the negative gate voltage, it doesn't have any operation at negative gate voltage. So coming to VG is equal to 0, almost the drain current is 0. And when the gate voltage is increased in the positive manner, the drain current will be increasing in its value. So it will be having only the enhancement mode operation. And this is the magnitude of the drain current. So this is the transfer characteristics for an enhancement mode MOSFET. Similarly, when you come for the drain characteristics, which is drawn between the drain source voltage and the drain current, it works only for the positive gate source voltage. So for the given gate source voltage, the value of the drain current increases and it gets saturated at a value. So it works only for the positive gate voltage. So this is the enhancement type MOSFET. So since it doesn't have the minimal value of threshold current at VG is equal to 0, it is normally called as a normally off MOSFET. And it doesn't have a physical channel. So the charge carriers that are emitted by the source terminal reaches the drain by forming a physical layer, physical inversion layer, which acts as a bridge in order to convey the charge carriers towards the drain. And with the increase in the gate source voltage, the magnitude of the drain current increases. And coming to the application of MOSFET, MOSFET can be used as a low power, high frequency switching device. So it is very well used in the inverter circuits. And it is used as a high frequency switching device in case of the fax devices, where fax devices are the flexible AC transmission systems. So the main application of the MOSFET is low power, high frequency switching device. And it is very well implemented in the inverter circuits. So that's it about the MOSFET. And next, let us just move on to the BJT, bipolar junction transistor. Coming to the bipolar junction transistor. So already we have just discussed about the PN junction diode and Zener diode. So which is actually formed by taking a P-type and an N-type layer and combining them together, which is forming one junction. So if you just see the construction of BJT, if a PN junction is taken and if a P-type layer or to the existing PN, if an N-type layer is added, then there is a possibility for us to have the construction of bipolar junction transistor. So here, this is called as PNP transistor and this is called as NPN transistor. So the terminal which is located below is emitter terminal and this is the base terminal and this one is the collector terminal. Similarly, in case of the NPN transistor, the terminal that is drawn from the N layer which is at the base is the emitter terminal, which can be denoted with E, and the middle layer, the terminal drawn out of it is the base layer and the other one is the collector layer, collector terminal. So coming to its symbol, it is the base which combines the emitter with that of the collector, and generally base is narrow, emitter is wider, and collector, comparing the area of the collector, the collector is much more wider than the emitter. So here it is the base terminal, emitter terminal, and the collector terminal. So how to identify the type of the transistor? It all depends upon the direction of the conventional current. If the emitter current is flowing away from the junction, then it is the NPN transistor. And if the emitter current is flowing towards the junction, then it is called as PNP transistor. So here there are two junctions, junction 1 and junction 2. So in order to have the flow of current from emitter towards the collector, it is necessary for us to have the condition of both the junctions in forward bias. So it is the emitter which emits the charge carriers and which is being collected by the collector terminal. So these are the basic terminals and this is the symbolic representation of the NPN transistor. So now let us discuss about the working principle of BJT. So the working can be classified into three regions. One is cutoff region. So in cutoff region, both the junctions J1 and J2 are forward. J1 and J2 are reverse biased. So in case of active region, junction J1 is forward biased and J2 is reverse biased. In case of saturation region, both the junctions J1 and J2 are forward biased. So now let us have the discussion about its working principle with the circuit diagram. So before we proceed to that, let us just see what are all the possible configurations do we have. So we have three configurations depending upon which terminal is taken as a common terminal between the input and the output. If emitter is common to both input and output, then it is called as common emitter configuration. So if collector is common to both input and output, then we call the configuration as the common collector configuration. If base serves the common terminal between the input and output, then it is called as common base configuration. Out of these three configurations, it is the common emitter configuration which is very frequently used because of its high current gain. So its current gain ranges from 10 to 100. And in turn, out of NPN and PNP transistor, it is the NPN transistor which is very frequently used in the real-time applications. So now let us have a discussion about the working principle of a common emitter NPN configuration. So coming to its circuit diagram, so we have the base emitter voltage and we have the emitter terminal, and this is the NPN transistor and this is the base resistor. Then we have the collector resistance connected to the collector terminal RC. So this is the collector terminal, emitter terminal and the base terminal, and the voltage is applied across the emitter and the collector terminal. So we see. So now it has two junctions which need to be forward biased if we need to have a flow from the emitter towards the collector. And it is the base current which flows through, and it is the collector current. So as per the Kirchhoff's current law, IE is equal to IB plus IC. So the output current is IC and the input current is IB. So initially, a magnitude of voltage is applied across V by VBE in order to overcome the barrier potential across J1. So it is not sufficient. So thereby, the base current is very less. So if the characteristic graph is drawn between the base current and the VCE, we can just see this is how it existed. So initially, the VC voltage is existing across both the junctions. Thereby, the applied voltage of VBE is not sufficient to drive the base current. So it is very clear that VCE is greater, during which IB value is very lesser. So as the magnitude of VBE is increased, the VCE gets reduced and the IB value is increased. So initially, it is the cutoff region during which both the junctions are reverse biased when VC magnitude is more, during which the IB is very lesser. Then, as we increase VBE value more and more, we just have the first junction to be forward biased, whereas the second junction is reverse biased. So during which the VC voltage gets reduced and the base current rises in its value. So this region is called as active region, and still the magnitude of IB is not sufficient enough and it doesn't reach the collector. So now in the saturation region, the applied voltage VBE is sufficient and VC is very much lesser, so that both the junctions are forward biased due to which there is a steep rise in the output current, which is the collector current. So in this is the region during which both the junctions are forward reverse biased, and this is the region during which one junction is forward biased, and this is the saturation region during which both the regions are forward biased, due to which the base current has increased in its value. So coming to the characteristic graphs, input-output characteristics. Input characteristics is drawn between VBE and IB for various constant values of VCE. So if you just look at, initially, it is required for us to spend some magnitude of VBE in order to reach the barrier potential and to overcome to make the rise in the base current. So it is this magnitude for the given value of VCE1. Then as we proceed with the second constant value of VCE, then again some magnitude of VBE need to be spent in order to overcome the barrier potential and to force through the current. So this is VCE2, where VCE1 is lesser than VCE2. So this is the input characteristics. And coming to output characteristics, it is drawn between VCE and IB, VC and IC for various constant values of base current. So as we increase the magnitude of base current, the collector current gets increased and gets saturated in the value. And if we need to increase the collector current much further, then obviously we need to go to the next constant value of base current. So it starts from IB1, IB2, IB3, and IB4, where IB1 is lesser than IB2, and it is lesser than IB3, which is lesser than IB4. So this is the output characteristics, and this is the cutoff region. And active on the saturation region. So here, this is the output characteristics of the bipolar junction transistor. So coming to the application of bipolar junction transistor, it can be very well used as an amplifier. Why? Because the common emitter configuration, particularly the NPN configuration, has a very good current gain ranging from 10 to 100. So beta is the current gain, where it is the ratio of the output current IC to IB. So if the current gain is 100, say for example, then if the base current is of 1 milliamps, then there is a greater possibility for us to obtain 100 milliamps as the output current. So this will be very much helpful for us in the transmission systems while we are transmitting the signals, because as the signals are being transmitted, the signals become weak. So where it is required for us to amplify the signal and to retrieve the information out of it. So this bipolar junction transistor can be very well used as an amplifier. So these are the two transistors that is existing as per the syllabus under the power semiconductor devices. And next, we can just have a discussion regarding the voltage regulator circuit. What do you mean by voltage regulator? You might have heard about the voltage regulator. Voltage regulator is that which is capable of maintaining the voltage constant irrespective of the changes that is happening at the input end or at the output end. So you have the idea regarding the Zener diode. So voltage regulation is a very good application of the Zener diode. So coming to voltage regulator, so it regulates the voltage, it maintains the voltage, whatever might be the changes that is happening at the input end. So there are two types of voltage regulation. One is line regulation and other one is load regulation. So how can we use the Zener diode as a regulator? So Zener diode is so fabricated that when it is in the reverse region, it doesn't conduct until it reaches the breakdown voltage. And once after reaching the avalanche breakdown, it maintains the same breakdown voltage as a constant voltage across the device. So this feature of the Zener diode is very well helpful to be utilized as a voltage regulator. So now let us come to line regulation. So if you observe the circuit, let us take 0 to 30 volt source. And whenever we just draw a directed arrow across, it means that it is variable in nature. And whenever do we connect any of the diodes, it is very important for us to connect through a current limiting resistance. So let us connect a current limiting resistance, which is of 330 ohm. And let us connect to the Zener diode in the reverse region. So what do you mean by reverse region? So the reverse bias is that when the cathode is connected to positive and anode is connected to negative. And now the Zener which is in the reverse bias is exactly connected across the load, across which do we need to maintain a constant voltage. So if you just look at, we can observe the voltage across to see what is the variation of the voltage. So now let us have a 1 kilo ohm resistor. So now if you just see the characteristic graph or the model graph, it is drawn between the input voltage and the output voltage, where the voltage, as we increase the input voltage, it increases and gets saturated finally in the Zener breakdown voltage. So if you record the values considering a tabulation between V in and V out, that is the input voltage and the output voltage, the voltage will be increasing and finally it will be settling at its breakdown voltage. Say for example, if the Zener diode is having a breakdown of 5 or 5.5, then with the increase in the Zener input voltage, the output voltage will be retaining at the same 5. So this is the model graph for the line regulation. Next, let us come for load regulation. So what do you understand from line regulation? We make a variation in the input voltage, meaning to say that irrespective of the changes that is happening at the input end, the Zener diode is capable of maintaining a constant voltage across the load resistor, which is observed from this curve. Coming to load regulation, the same connection such that now we are going to maintain the input voltage constant, say for example 10 volt, and we are going to make the changes in the output voltage. So we are going to make the changes in the load resistor. So now we are going to change the load resistor, and we are going to observe whether the constant voltage is maintained across the load resistor or. So in this, we are going to take various values of load resistors, and we are going to observe what is going to be the output voltage. So if you observe the model graph, which is drawn between the load resistor, which is in kilo ohms, to that of the output voltage, it settles itself in the Zener breakdown voltage. So let us take a value of 1 kilo ohm, 2.2 kilo ohm, 10 kilo ohm. So if the breakdown voltage is 5 or 5.5, it just maintains the same value throughout, whatever might be the changes that is happening at the load. So here in this case, it is regulating the line end, whereas here in the second case, it is regulating the load end. So that is how Zener diode is very well utilized as a voltage regulator based upon the feature that it maintains a constant voltage soon after its breakdown in its reverse region. So I hope you might have got a better idea regarding the power transistors MOSFET, bipolar junction transistor, and the design of the voltage regulator using the Zener diode. Thank you.